7.3 volumes, our final section. I have decided, in honor of our final section, to not give you a quick quiz this week or on this section. So we are going to jump right into the content and go from there. We are talking now about volume. So this whole span of time so far, we've just been discussing area, and that the area is the integral, or the area under the curve is the definite integral. So now we're talking about volume, and so we're adding another dimension to this. The volume of a solid with a known integrable cross-section area, A of x, from x equals a to x equals b, is volume is equal to the integral from a to b of a of x dx. What we are doing here is we are taking an area function and we are integrating an area function. So essentially, we are adding another dimension or multiplying by another dimension to find volume. And that really is all that volume is. When you think about the volume of a box, you take the area of that box, the base times the length times the width on the bottom, and you multiply that area formula, length times width, times that third dimension height. And that is, in essence, what we are doing. Let's say, for example, we are asked to find the volume of a pyramid. Now, I know that you know that the formula for the volume of a pyramid is length times height times width divided by 3. But we're going to use calculus now to find the volume of that pyramid. Consider the horizontal slice through the pyramid. So if I would, in essence, take this pyramid and slice it up horizontally so that I kind of have a loaf of bread, what would the shape of each loaf of bread slice be? We would find that the shape of that slice would be a square. So the volume of that slice is the area of the square times the change in the height, because I know that this slice that I have has an area of s squared times then that little change in the height, which is dh. If we put a 0 at the top of the pyramid and make down the positive direction, then s is equal to your height. So the volume of a slice is h squared dh. If I integrate that over 0 to 3, the integral of h squared, or the antiderivative of h squared, is h to the third over 3, and then I'm going to integrate it from 0 to 3. I will get 9. Well, I know that 3 times 3 times 3 is 27, and then I cut that in half, or I'm sorry, by a third, and I will get 9. This correlates with the formula volume equals 1/3 big B, the area of the base, times your height. So here is our method for finding the volume if I know the shapes of the cross sections, or as I like to refer to them as the slices of bread. Number one, you want to make sure you sketch the solid and a typical cross section and understand what this thing actually is, what kind of shape this thing is actually made up of. The second thing you want to do is find a formula for your volume by finding a formula for your area. So if I know the shape of the cross section or the slice of bread is a circle, I'm going to use pi r squared. If I know that the shape of the slice of bread is a rectangle, I'm going to use base times height. So you have to come up with that formula, and you want to put that formula in terms of x. 3 then is you want to make sure you find your limits of integration. That could be based off of an intersection point. That could be based off of limits that they actually tell you in the problem. And then number 4, you want to integrate your volume, or integrate your v of x to find the volume. So I wanted to Okay, so I would like to take a second now and just show you some different situations that we may have. What I have here is, if you can kind of see, oh, looks like I can maybe turn it. All right, looking straight on, you can see that this is made up of two parabolas. So I have a parabola that is flipped and a parabola that is not flipped, and I'm talking about the shape that is formed by the intersection of those parabolas. So let's kind of put this back on its side. If I would take my loaf of bread and I would slice it up so that each slice now has a shape, those slices' shapes would be all rectangles. So now I can find the height of that rectangle, which might be fixed. It might be two, well, it looks like in our case it's 1 unit tall. So the height of each of these rectangles is 1 unit tall. And then the base of those rectangles is the distance of the one function minus, of the top minus the bottom function. So I would just integrate my height of 1 times the top minus the bottom function over those intersection points wherever it would happen to cross. Now, let's kind of look at a situation where it might not be rectangles. What about squares? So now I cut up my loaf of bread and each slice is a square. So my height is going to be the same as my base. Now we've already determined that the base is the top function minus the bottom function. Well, that would be the same then for your height. So I would just integrate that formula over those intersection points. Let's look and see what circles look like inside of this. So here are circles. All my slices of bread are each a circle. So pi r squared. So my radius would be half the distance of the top minus the bottom function. So pi times the top minus the bottom in half squared would be what my integration formula would be. Semicircles, you can see that would just be pi r squared divided by 2. And then we have triangles. That looks pretty cool. Kind of looks like a helmet of some sort. But then triangles would be base times height. And it looks like those are heights that are changing over the course of that interval. And so they would have to give you a little bit more information, or they'd have to tell you that they were equilateral triangles or something for you to come up with the height function and then integrate it. Let's talk about another concept. Suppose we start with this curve, and this curve is the square root of x. My boss at the Acme Rocket Company has assigned me to build a nose cone in this shape. So I put a piece of wood in lath and turn it to a shape to match the curve. And so you can see that by making it now rotating around the x-axis, we have made a 3D image, and we're going to try to find the volume of this particular cone. One way would be to cut that cylinder, or to cut this nose cone into slices of bread like we did. And it should follow to you then that if I would do that, all of those cross sections would be circles. Okay? Well, I know how to find the area of a circle. Pi r squared would be the face of that circle, and then to multiply it by that little dimension would be a change in x, or dx. So in this case, r, our radius, is actually the y value of the function. So we have pi times the square root of x squared, and then the thickness is a small change in x, which is going to be denoted by dx. So what we're going to do is we're going to integrate it over 0 to 4, the length of the function over that interval, of pi times the square root of x squared dx, which is just the same as pi x dx when it's simplified. So your antiderivative is pi over 2x squared. When I put 4 in, I'll get 8 pi. When I put 0 in, I'll get 0. And so I get an answer of 8 pi. So that is the volume of that nose cone. This application of the method of slicing is called the disk method, obviously because you're forming multiple disks. And the shape of the slice is a disk or a circle, so we use the formula for the area of a circle to find the volume then of the disk. If the shape is rotated around the x-axis, then the formula is going to be the volume is equal to pi times the integral from a to b of y squared, y meaning the value of the function at that point, dx. So this y is still going to be in terms of x. We're just denoting it by saying that y equals whatever that function is. Since we'll be using the disk method to rotate shapes about other lines beside the x-axis, we're not going to have this formula on any kind of quizzes or tests. It's going to start to become second nature because you know that the shape or the area of any circle is pi r squared. So you should be fine and not worrying about memorizing that. It should come naturally. A shape rotated around the y-axis would be integrated with respect to y. And we have here x squared, but don't think that it means that our function is in terms of x. It will actually be written in terms of y when we solve it for x. Okay, so we are finding the volume of this region rotated around the y-axis over the interval from 1 to 4. So if we just pick some points and we graph them, we can see what the shape is here. And we can revolve that around the y-axis. And that's going to create a horizontal slice of bread. So that thickness of your radius is going to be your change in y, or dy. So now everything's going to be integrated with respect to y. The radius is the x value of the function. Hopefully you can see that right here. The radius is that distance from the axis to the function. So we're going to integrate from 1 to 4 pi times 1 over the square root of y all squared dy. This represents the volume of the disk. Okay, when I simplify it and throw that square in, I'll get 1 over y, which gives you pi times the natural log of y from 1 to 4. I don't have to worry about the absolute values there because my 1 and 4 are both positive anyway. And so natural log of 1 is 0. Pi times the natural log of 2 squared is your answer. Or 2 pi natural log of 2 when you pull that square root from the back to the front. So here is kind of a situation where this would be the case. The natural draft cooling tower shown at left is about 500 feet high, and its shape can be approximated by the graph of this equation that's revolved around the y-axis. So here's an example of an equation that if I would revolve it around the y-axis, it would form that cylindrical shaped tower. The volume can be calculated using the disk method, again, because our slices of bread are going to be circles. And so I'm going to integrate it from 0 to 500 because that's how tall the tower is. And the radius is the value of the function. Or actually, it's not a function, but the value of x at each of those y values. And if I throw that on my calculator, we get that it is 24,700,000 cubic feet is how much it could hold. The region bounded by y equals x squared and y equals 2x is revolved around the y-axis now. Find the volume. So we're going to rotate it, and you can see that it forms this cone with this V shape inside. Okay, and we need to figure out the volume of the actual shape, not how much it's going to hold, but actually what is the volume of the materials used to make that shape. So we're going to use horizontal slices again. And now you can see that each of my slices are going to have a hole in each of them, so it looks like a washer. The disc now has a hole in it, making it a washer, and the volume of that washer would be pi big R squared minus pi R squared times your thickness, which is going to be dy. So we have the radius all the way out from the radius of the outer circle would be big R, and the radius of the smaller circle that we're going to subtract away is going to be little r. And then our thickness is going to be our change in y. Alright, so we have to put everything in respect, or with respect to y, so we're going to solve these now for x, because I'm integrating with respect to y, so I have my volume equaling the integral from 0 to 4 of pi times big R squared minus little r squared dy. When I integrate that and I find my antiderivative, we end up getting 8 pi over 3 as our answer. This application of the method of slicing is called the washer method. The shape of the slice is a circle with a hole in it, so we subtract the area of the inner circle from the area of the outer circle. Be careful that you do not say that r squared minus, or big R squared minus little r squared is actually the quantity r minus r all squared. Remember that exponents do not distribute it in because pluses and minuses mess it up. That's a very simple mistake that people will oftentimes make. Like the disk method, this formula will not be on formula quizzes. I want you to understand how the formula works. So now we're going to take the same region and rotate it around the line x equals 2. Okay? So now it's going to form a cone with a concavity situation inside of it. So our radius is actually, our big R is actually 2 minus the function y over 2. And then the inner radius is 2 minus the square root of y. So when we integrate that, we're going to integrate it still with respect to y because we're rotating it around an axis that is vertical. And go through and I find these, sorry, I'm rushing through this, 8 pi over 3 is the same. I have a watermelon right here, and what I'm going to do is change the function with these sliders so that the function matches, or the shape of the ellipse matches the watermelon. Okay, so that's not too bad. So now what we have is the top half of our watermelon. So I'm going to take my watermelon out, and we've seen that the top half of this watermelon is the ellipse with this as the equation. Okay? And when I rotate it around the x-axis, you can see that I do have the shape of the watermelon. And if I know that my radius is the height of the function, so each slice of this watermelon is going to be a circle. So it's pi times the function squared, and I'm going to integrate that over 0 to about 22 or so. Okay, I have another function here, and this function is an x to the fourth. Here's the function. We can see that it is an x to the fourth, and what I can do is revolve it over the x-axis, and you can see that it will form some sort of a vase, and we can find the volume of this vase by integrating it over x sub 1, which is negative 1.512, to x sub 2, which is 1.327. And when we integrate that, pi r is going to be the value of my function, all squared, the volume of revolution is going to be 13.523 pi. And so that is about how much that vase will hold. Okay, so that brings us to the end. We are officially all done, everyone. Great job, and watch this, and we will see ya tomorrow. Bye.